Don't talk
We go ahead and start.
Sure. I'll just sit down for a minute.
What we're doing is, why don't we go around here and let everybody introduce themselves. I'm Andy Dozier. I'm now retired. I have taught capstone project course at IEEE here for 5 years. Worked with the networking and communications. Part of that was capstone course project. So I assume everybody in here is either an ECE or CECS major, or any who are not. Okay. So what I'd like to do is just go through and have each student introduce yourself and tell me what your academic major is, what your co-op experience has been. Let me get some idea of the experience level of the audience here. We'll get started.
All right, I'm Andrew Bruley. I'm a senior electrical engineering student. My last academic semester, co-oping at CUTA. Got one more, and I'm graduating.
Are you gonna do a master's?
I'm considering.
Okay. Make sure you get this a research fellowship so you don't do it on your money. Somebody else.
I'm Maxwell Jones. I'm a senior, graduation May 2020. I completed all 3 of my co-ops at First Flight Automation, who handles controls integration for automated conveyor systems.
You're in Hancock.
Yeah, pretty much.
I hope you're not in Alabama.
I wouldn't know much about that. I had time to pay attention to
Their mascot is a big red elephant. Okay, sure.
I'm Nathan Hodges. I'm a senior ECE student. I did all 3 of my co-ops at CUTA. So,
My name is Lee Wood. I am a senior AC student. I did all 3 of my co-op at the Coal Touch System. Actually, my first day of co-op was Andy's last day of co-op. So,
Convenient, isn't it?
yeah. So, yeah.
Okay.
My name's Mariah Owens. I'm a sophomore doing my first co-op at CSI.
Joshua Gillespie, sophomore, and I'm starting my first co-op in Springfield.
Great.
I'm Jacob Butler. I have no idea what I am as far as grade level wise, but so far I'm quite fine. Several counties over. But I'm starting my first co-op at Lab Tech next semester.
Okay. Look up Mike Gray. He's a former student of mine. And a former employee of Control Touch. All right. Let me turn off my voices here. I apologize. Yes.
My name is Dave Al-Assad. I'm a senior electrical engineering student, and all my 3 co-ops with North American Stainless.
Is your control engineering background as well, or you not?
There's a bunch, like I did a lot of the maintenance that I did is mostly with PLCs and HMI systems. So
Okay.
And I'm Mark Allen, senior electrical engineering. I've done 2 of my 3 co-ops at Alliant, which designs hardware systems for,
No line.
and I'm actually looking for a 3rd one. I'll be done academically next semester.
Okay. How many of you all know Mary Andrade in the back? Let's go. She's a very helpful lady when it comes to getting employed. What I used to tell my students is, you may not believe this, but your parents don't want you back. After you graduate. We left off 2 up here.
I'm Caleb Byram. I'm a senior electrical engineering student. I've done all 3 of my co-ops at LG&E Project Engineering, and I'll be graduating next semester.
Did you ever run into Nick Jewell or any of those guys? Jason Van? Okay.
Hello, I'm Nathan Shim, also a senior electrical engineer. I did all my co-ops at Lab Tech.
Okay. A lot of control companies, co-op realm. Are you in touch with all those companies? Where are the CECS students? Are you a CECS student? Good for you. You got one. This has been a pet peeve of mine because, in the ECE department, I would always need strong software developers. And the ECE students tend to be more oriented towards hardware than software, or at least at microprocessor level. I'm sure that's changed since I've been gone. So I'm here representing the IEEE, basically, and we're trying to re-engage and revitalize student activities here at UL. Because we believe it's a service profession, but also it may not be, you may not realize this, but the best way to get involved with your profession is through a professional society. So how many of you know about the IEEE meeting tonight? Everybody not know? Okay, it's at the University Club at 6 o'clock, and the admission for students is $5. It'll be a good meal. It costs the IEEE $36 a student per person. Okay? But if you'd like to come, we'd be happy to have you. So, how should we do the slide flip? Are you gonna be in the flipper? Sure. Okay, let's go to the next slide. This is my background. As you can tell by the amount of gray hair I have or have lost, I've been around for a while. I graduated in 1974, and I started out as a material scientist and was hired as a process engineer at TRW. Everything I've worked on my entire career has been electronic components and communication. And as I progressed up through my career, I became a project manager. And then in 1998, I got a call from my former advisor. I was working in Huntsville, Alabama at that time at TRW. And, they needed somebody to teach a course in project management, which I then did, and that turned into a second career because at the same time, ABET required capstone project courses. You may not believe this, but that hasn't always been the case. That came in the year 2000, about the year y'all were born. Or maybe 2 years old. So, so anyway, there's a big problem that a lot of the universities had, engineering school programs did not have a senior project course. If you've ever read the ABET criteria, they want students to be able to communicate effectively, work in teams, and build complex systems. Students never got exposed to the design and integration of the system. So that's where the courses came from, and also industrial involvement was really important. And that's how I ended up at U of L. I grew up in Louisville. I always wanted to retire in Louisville, but I was in 2009. I moved up here and started working at U of L. Did that for 5 years. I still needed to keep working for personal reasons, and ended up working at Control Touch for 4 years. I'm going to pass this around. This is something we did in Control Touch. This is a PLC with 2 push-button assemblies and a few other modules, A to D module, D to A, and so forth. And that PLC sells for about $350. I wish I'd known about that when I was teaching capstone course, because basically, one of the things that you always run into are limitations on I/O. And you don't have those kind of limitations on PLC. You have tens of thousands of I/O points, depending on how the system is designed. So Mike Harris, who is the fellow that I work for, designed this assembly that you see here for Engineering 111. So specifically, I have a whole bunch of modules that I put together in Mike's guidance. And Mike will be there tonight, probably. And this is a perfect platform for teaching PLC programming. That $350 includes the software development environment, which runs on your laptop. It's a large program, but it runs on laptop. Let's go to the next slide. So basically, what I found, it's less true with U of L, but it's certainly true with engineering schools that don't have co-op programs. The students are not exposed to hardware as it's implemented in industry. And in the old days, when I got out of school in the 70s, it was understood that an industry would, or a company would spend a couple of years getting students coming out of engineering school trained up where they can be productive and be useful. I don't know what you guys are seeing on the job market, but right now, what I've seen is that what companies want to do is they want to hire an engineer with about 3 years experience, because they don't want a fresh out kid that doesn't know anything about what they do. They want them to hit the ground running to be productive first day. So that presents a challenge. How do you get experience without a job, and how do you get a job without experience? And so that's where the co-op program comes in, and I think it's extremely beneficial. And y'all may not even realize that when you enroll, but it's a big plus. So what I wanted to do with this particular lecture is relays are extremely important in the design and implementation of a control system. And I wanted to go through some of the history of this so that you can understand where this all came from. So back in 1830, there was this thing called the telegraph. Does anybody in here know Morse code? Anybody in here a ham radio buff? Got one. Okay. Well, students now, because they can use a laptop and a cell phone, think that they're computer operators, computer programmers, designers, but that's not really the case. But Morse code is the beginning of digital communications, where you close a contact and you open a contact. The amount of time it's closed or open determines the numbers and letters that you're sending across the wire. Well, what happens is, after some number of miles, the signal gets degraded. And that's just because of the inherent resistance of the wiring. So they needed a way to regenerate the signal. The thing that's interesting about digital communications is that it can be regenerated faithfully to its original fidelity. So that's why the whole world was going digital. That wasn't always the case. So anyway, in the next slide, this is the operator station of, it's an actual antique of telegraph operator. And in the next slide, you can see this is a relay which was used to regenerate that signal in 1830. So that's getting on towards 200 years ago. Mostly before my time. So let's go to the next slide. So today, then, what happens is these relays are used to turn motors on and off, and do a variety of things, which I'm going to talk about. And so the whole idea is when you get down to having to change voltage levels or something of that nature, or to turn a motor that draws a lot of current on with a low voltage, like push button, then that's how you do it with relays. And some of these relays can be quite expensive, thousands of dollars. So we'll, if you go to the next slide, let me tell you about the PLC professor first. This is a gentleman who was responsible for developing training materials for Allen Bradley. That is an Allen Bradley PLC. There's 2 or 3 manufacturers of PLCs, and I don't know all of them, but Eaton, Cutler, Hammer, I'm sure has a line. And in the United States, Allen Bradley PLCs are, I think, about 70% of the implementation of it. So, anyway, this guy developed these training materials, and he's got a fabulous website called plcprofessor.com. And you can get all of his lectures off of that website. So let's go to the next slide. So here's a relay. This is about the size of an ice cube, or what used to be called a flash cube. Anybody ever seen a flash camera? A camera with little flash bulbs that spin around. So what you have here, you don't have a pointer by any chance. What you have here is a coil, which is a monstrously large part of the device, and up at the top you have contacts. The next picture, the picture beside it is the what plugs into a printed circuit board or a socket, so that you can actually make use of it. Next slide. So these are the different pieces and parts. That's pretty simple, isn't it? I mean, this is a pretty simple switch. You've got light switches over here. So you switch that on and off, lights come on and off. Seems simple. Let's look at the next slide. Here's another set of blow up of the contacts. So what you got here is actually two switches. One's normally open, one's normally closed. Let's go to the next one. And so this is a schematic of that same relay. So when the coil is not energized, then you have the normally closed contact at the top. Next slide. When the coil, I'll have to go to the next one after this. So notice that the top contact is normally closed, the bottom one is normally open when the coil is not energized. So let's go to the next slide. So basically what happens when we energize the coil, i.e. with 24 volts on it, then it opens the top contact, closes the bottom. Now, believe it or not, PLCs were developed to replace huge racks of relays. Because all the electricians understood relay logic. So they would have, refrigerator size or even bigger racks just full of these relays. And they were used for industrial control applications. So back in the 70s, GM wanted to replace that capability with a programmable device, and that's where the PLC came from. So let's go to the next slide. So basically, you're talking about opening and closing switches. Now, I might also mention, transistor is works the same way. So there are solid state analogs to relays. So here is an example of a couple of different poles and throws configurations. So, students don't get exposed to this because it's too mundane. This is technician stuff here. But I will challenge you to go in and try to wire up and assemble and put together one of these big control cabinets. I mean, to go from a line drawing on a CAD terminal to a cabinet that's 7 feet tall and 12 feet long. It's a challenge. But here are different configurations of single pole, single throw, double throw, and so forth. And there's the relay and switch association, there's 23 different configurations that you can get. Now, if you take a look at the next slide, here's an example of a relay that has 4 sets of contacts. So when you energize this coil, you're actually opening with all 4 switches. So you can switch 4 things on at one time. Now on that PLC, you notice the push buttons. Push buttons have in them an LED light. So when you push on the button, you're opening a contact, and then the light can illuminate. It doesn't have to illuminate. So when you push on the button, that's the input to the PLC. The light turning on is an output to the PLC. And the thing to understand is that in any control system, you've got control stations all over the place that have buttons, usually start and stop, sure, sometimes alarm silence or something like that. So all this stuff has to be controlled by software. Next slide. So then typically what happens is your control circuits are 24 volts DC. So when you push the button on that contact, you energize the coil, and then something happens. You have to indicate that on the human machine interface software. The operator knows what's going on. I've actually got an example I can show you that's real simple-minded, but it took about 6 months to get it built up in Philadelphia, at the airport of Philadelphia. So when you close that contact, something has to happen, or something should happen if the software is designed properly. Typically, a light comes on and you can start up the motor. Now, how many of you have played with a variable frequency drive? That's impressive. 3 out of what? 12 or 15. You'd be amazed. Here's another example of a device that is not encountered, not seen, but they're used all over the place. And these VFDs, again, are very expensive. They can be $1,000. Just
That's similar to PWM.
it basically changes the frequency, which changes the speed of the motor. Okay. Everything's, DC at that point. But the other thing is on a conveyor, for example, you want to start the conveyor up very slowly, because if you hit it with all the energy of the motor, it'll tear stuff up, literally tears up areas. Not to mention anybody that's standing close by. So usually what happens is you push a button, the alarm goes off, the conveyors start up slowly. They don't all start up at once.
It's like the airport baggage stuff.
Right, exactly. So it sounds pretty simple, doesn't it? Would you believe you can make a career out of this stuff? And that there's a whole lot of jobs in the city of Louisville, the metropolitan area, that allow you to do this. How many of you are married? How many of you don't like to travel? Don't get into the control engineering business if you don't like to travel. But you gotta go wherever the control system is. And like it in Control Touch, we had systems we were installing in Fort Myers, Florida, Anchorage, Alaska, Hawaii, and up in Philadelphia, and way up in Maine. I had one job at International Falls. You don't want to go up there in the winter time. It's the coldest spot in the United States. But we did end up going up there in the spring when it was in the 30s instead of -3. Okay, next slide. So this is a real simple circuit. You close the contact, that energizes the coil, and the red light comes on. That's basically what you have sitting right there on the desktop. Now let's go to the next slide. I'm sorry. The switch was open and the red light was on. Now you close the contact, you energize the coil, it opens the top contact, it closes the bottom contact, and the green light comes on. So basically then, the push button is the switch, that's the input, and the lights are the output. So it's pretty simple. And there sits an assembly that will do exactly that for you. Next slide. Notice, however, that the coil has 120 volts AC on it, whereas the lights have 24 volts. So you got to be aware of voltage. So when you look at control drawings, you'll have a 24 volt DC drawing, you'll have an AC drawing with different voltages. Next slide. Okay, so this is all done under PLC control. And let's go to the next one. And so the idea then is, all this stuff, the design, the design process works as follows. How many of you know an architect or have known architects? Well, they're art type people. You know, they design a building like this, it looks nice. They don't necessarily think through all of the stuff they gotta get that building to do. Well, when you're designing like an airport or distribution center, has anybody driven by the distribution center out in Jeffersonville? Amazon distribution center?
Work there.
You work there, okay. Have they got any conveyors running around there?
Well, they've got enough, you compare it, a lot of them are actually more roller lines. That they start stopping individual segments.
Yeah. So everybody thinks that because the internet, you can now order stuff on the internet and it just shows up on your doorstep, that you don't need more retail stores anymore, do you? What do you need? You need FedEx, UPS, you need distribution centers, you need all kinds of trucking and logistics to get components or parts, clothing, whatever, from wherever it's made, to wherever it's gonna be distributed. And, so anyway, the architect designs the building, but the mechanical designer figures out what conveyors are required. Before that's even done, like in a baggage handling system, they do a system engineering study. So as an example, the airport in Las Vegas has 48 million passengers a year. So you can imagine how many bags that need to get checked in or they can get picked up. And so what happens then is the mechanical designer does a layout and based on the TSA study, which is based on heat flight loads that are coming into and leaving the airport. And then the control engineers have to come in and figure out how all this stuff works. They have to develop the software, have to integrate the system, have to test it. That's the subject of tonight's presentation, probably. And this is all, the way this is conveyed between companies, between engineers, is with drawing, engineering drawing. How many of you like to draft? Oh, we got one. A couple. Well, there's a big art to putting lines on paper, when that line might mean that you've got to make a 200-foot long conduit run out to the conveyor. So what I wanted to do with the rest of the slides here is just convey to you what the symbology is in the software on the PLC and what the part looks like physically, and then how that would be enacted in a drawing. So here's a couple of examples. This is actually from control drawing. So you've got, this is your 120 volt AC bus, and this might be a whole page of stuff with hundreds of connectors on it. You've got a switch, which is a push button. You've got the coil, which is the circle. Let's go to the next slide. So here's how that's shown in the drawings. The top one is normally closed, the bottom one is normally open. Next slide. And so this is kind of an animation of what would happen when you activate a contact and activate the voltage. So in this case, the red light is on, the contact is normally closed, the green light is off, and then the state of the coil changes, it's energized, and the green light comes on and the red light goes on. So that's what the drawing might look like. Next slide. So the other thing that you have to do is, this may look trivial, but these wire terminals here, I think there's 24 inputs and some other smaller number of outputs on the PLC. You've got to use the same nomenclature on the drawing that you're going to use to wire everything up. And then in the PLC development environment, somebody has to take those drawings and develop software that actually implements the functionality that you want to have happen when you start the system up. Naturally. So here's an example of a coil. So the physical device looks like it does on the left. And then on the ladder diagram, which is the primary, how many of you have played around with ladder diagrams? Okay. That is an extremely important thing in an interview in control engineering. But that's what it looks like in the software that you use to develop the program. And the reason ladder diagrams exist is because electricians could read those. And it was something they were familiar with. So they wanted to give them a programming environment that they were familiar with so they could use it and they could be productive. Students learn other things like C++, maybe Visual Basic, other high-order languages. You can indeed program PLC with those languages, but it's a little trickier than using ladder diagrams. Most control engineering companies use ladder diagrams. Next slide. Here's the push buttons. Normally open, normally closed, and this is what they look like on the ladder diagram. Next slide. And here's the contact. Now what you can't see here, there's a contact, there's actually 3 contacts that are underneath those push button assemblies. One is the light, and then you've got 2 other normally open, normally closed contacts when you push on the button. So the device is on the left, the control drawing schematic is in the middle, you'll see ladder diagrams on the right. On the bottom right, this is an actual screen scrape from the CCW software for that particular PLC. Let's go to the next. Here's the pilot lights. This is another module that snaps on this rail. These are DIN rail devices. And you can put in either a green or a red light depending on which color you want. And, the LEDs, by the way, are expensive. They cost something like $11 or $12 a piece. And if you leave them on forever, then they burn out. You have to replace them or send a replacement. Next slide. That's really all I've got for this particular presentation. I've got one more thing that I'd like to show. It ends up with, get back to the rest of it. I got one more demo. It's not started. They want full screen. Turn the volume up. We'll see if this will work. It's behind from the. Yeah. Okay, so this is an HMI for a control system. So basically the PLC is sending messages back and forth across the control network. And this is an actual live screenshot of the startup sequence. The sound is off. But what happens is you've got alarms, you've got sonic alarms. They run you out of this room if you've heard them. And then you'll see the carousel up in the top right. Well, first thing that happens, all the security doors open. Second thing that happens is the conveyors start one at a time. Now the operator, the baggage handlers are standing over here and they don't know that the system's even running until the conveyor starts. Then they start loading bags. It looks pretty simple, doesn't it? How long do you think that conveyor line was? About a quarter mile. If you ever go to Terminal F, the Philadelphia Airport, once you start it one more time. Basically, the bottom conveyors are in Terminal F, and the carousel is in another building across a 4-lane highway that's in and where the carousels are, where people pick up their baggage. So this whole startup sequence, you can see the doors blinking, that means that they're opening up. When they're green, they're open and ready. None of the conveyors will start up until the doors open. Now, the thing to understand is there's a lot of stuff that can go wrong. Like, is the door open or shut? You got a sensor to tell you. Got a magnetic sensor. That's handled by the security system guys. They install it. So if you get false alarm, meaning that the door is not opening, or the door didn't open because the security sensor didn't let it, then what happens is you get a phone call. And then you gotta get somebody on the airplane to go up there and figure out what the heck's going on. And it's a $10 relay, or the door's adjusted wrong. So that's it. That's what control engineering is all about. That's what the field engineers do. And so this was a small job. We had 2 conveyor lines. When I say small, I mean $1 million. It took about 6 months, and it was done in the winter. I'm like, hey, Philadelphia's not a good place to be in the winter time. So I'll throw the floor open to any questions if anybody has any questions. Yes.
So you're out there, when you get one of these jobs, how much of that 6 months is designing stuff here, and how much is being out and say Philadelphia installing?
I'm talking about 6 months to get it to work. Okay, then you have to do the design, then you have to get the panels built. Then you have to ship the panels to everything. Then they drop the panel off the fork truck. You have to build the panel again, ship it back. This actually happened on this particular job.
I mean, all fairness, I used to work for FedEx, and it's kind of weird, what anything gets anywhere unless.
No, this was not FedEx. This was done, I mean, we sent a dedicated truck up there, and the construction guys take the panels off the truck. Well, this is a construction site. And they didn't strap the thing to the fork truck. They tried to drive it up this wobbly, pile of dirt, basically. He said, well, it didn't fall too hard. It just kind of gradually, and when we got it back, all we have, these were the bottom. Pieces. We had to buy a new cabinet, a new door, I guess. Replace it. Didn't have to buy a new cabinet. It landed on the door. Yes, sir.
It's a better version of the question is, how much time in the field, how much time are you at the home location?
Depends on the company. See, a control touch, they would assign one engineer. Typically, you've got a design group. I can't talk about a line MHS and diversified, and maybe somebody else can comment. But the control touch, you had one group that did the panel design after they won the job. The project manager has to get involved, get all the material ordered. And then basically panels have to get built. Somebody has to, at that point, you send people out in the field, but most times when you get to the field, the electricians aren't ready. And the biggest delay in that 6 months was the electricians. I mean, there's miles and miles of wiring that has to be put in 2 buildings, okay? And so, then they ran into a problem with, TSA did not like the ingress and egress from the airport side into the baggage handling, or into the baggage pickup area, because that was, you had to go through security. And so they had to redesign that. I mean, it's just one headache after another. Now, they're not all that way, but like in the Las Vegas airport, we redid all of Terminal 3, and that was about a 2-year-long job. And I climbed over every damn conveyor in that damn airport. It's a while. I mean, I spent probably 6 months in Las Vegas. Now, it's not bad, dude.
When you're out there?
Huh?
Does the company pay for your housing while you're out there?
Oh, absolutely.
Okay.
Pay for your food. You got a $60 a day per diem for food. They pay your car and your hotel and all that. But, you know, it's construction jobs. You gotta work. You know, the electricians out there get paid $48 an hour. And it gets to be 120 degrees in the summertime. So they have to start about 6 in the morning. So, you know, you gotta be there when the electrician. And it's a union outfit, so.
Yeah. I think they're doing that right there, is how many union electricians do screw the light bulb?
Well, some of them are pretty good.
I'm trying, I heard them. Oh, yeah, never seen them stand up.
3. One to hold the light bulb, 2 to turn the ladder. So, that's a joke I used to hear about software engineers. Yes.
So we had discussed how PLCs ultimately replaced like racks and things.
Right.
And I was wondering if you had any sense of like where the state of the art might be evolving. Like, do PLCs seem to be going anywhere, or are we probably just going to be using those for
I
control
think,
systems like this for a very long time?
I think what you'll find is that these are industrial strength machines. And there's like, there's a company here in town that the name is escaping me, but they do railroad signals, which is another control type application.
Is it Siemens?
I guess it's Siemens bought the company. It used to be somebody else.
Siemens bought it. I don't know who it was.
Remember the name?
Was Safe Tram, I know I was interested in.
Yeah, something like, that's their product line, but that's the company that designed it. But like they were replacing stuff up in Brooklyn that was 100 years old, they still have relay racks. So, you know, these big legacy industrial utilities, companies like that, they're not gonna just fork out the whole sewage treatment plant control system and replace it. We did all the Lexington Fayette County control system for their sewage treatment plants or 85 pumping stations. And they're all connected by wireless radio. And the biggest damn headache, there are 2 big headaches, the wireless and the security engineers in the IT department. They want everything to come through them. But anyway, you run into a lot of interesting organizational issues. But I don't think you're going to see this technology. What you'll probably see is the software development piece will become more straightforward, possibly more automated.
That seems to be what's happening. Like, instead of ladder logic, it seems companies are like Allen Bradley and Schneider are making their PLCs more compatible with using like C programming.
Well, you can do
So it
that,
becomes a
but
lot more programmer friendly.
talk to Mike Harris tonight.
Okay.
Just ask him that very question.
Yeah.
Because ladder logic is a hell of a lot easier to troubleshoot apparently. Going through C program. But, I wouldn't want to be the guy that, I'm a project manager. That stuff's all hocus pocus magic as far as I'm concerned. But for you guys getting out, my pitch here is this is a fabulous area in which to work. It's very interesting. So as long as you don't mind traveling, you'll be fine. Yes, sir. Yes, ma'am, sorry.
What brought your interest in project management?
It was kind of a default, really. I first started out as an engineer. Then I became what they call a section head, which means I had 4 or 5 engineers working for me. Then I had a bigger section with 22 people, which included some technicians, building surface acoustic wave devices. And then, you know, what happens in these bigger companies is that the person in charge of that functional area, like the surface acoustic wave area, has to provide input to all the bidding and proposing of the projects that they're bidding. And the projects are won, and then the project comes to you, and they ask you to, you know, manage it basically. So, and then during the time I was at TRW, they actually had a, you know, week-long program where they'd send you to school on doing things their their way, project management stuff, which, by the way, evolved into something called the Project Management Institute. And they're all using the same techniques, it's earned value reporting. And that's required for government type jobs. And then I just kind of went from the functional side to the project side. But these are companies that are what they call matrix organizations, where you have a project part, you got a functional part. Functional parts usually own the labs, the employees that build specialized stuff. And then, so, you know, when I first, and then there's system engineers, they're the ones that design, high level design, and they eventually get it down to the nuts and bolts that you have to order. And I was the guy that had to order all the nuts and bolts and screws to get it to all work for my people did. And, project manager, if you've got a spacecraft that's gonna slip the schedule, slip the launch date, because your stuff isn't ready, you get more attention than you could ever want. So, you know, one of the guys I worked for became the head of NASA, it's Dan Gold. It's just kind of the way my career evolved. Yours might evolve very differently. Some people start their own business, like Mike Harris and Rick Dahl graduated from U of L, just started doing little projects for people that evolved into $20 or $30 million a year company doing these kind of systems. Then they sold the company, and they're both about 55 years old. I don't know what they're doing, but I'm sure they're counting their money every once in a while. But Mike Harris and Rick Dahl are two of the best electrical engineers I've ever met. They can do anything. Any other questions? Well, I would encourage all of you to come to the meeting tonight. One other pitch I'd like to make is Dr. Lee students, or the student branch, is we are very happy as a professional organization to help you do things in regards to your profession. We sponsor hackathons. We can put together, if you wanted to have a little short course in PLC programming. We've got 25 of those things over there in the engineering garage. I don't know if Dr. Robinson lets you use them, but you know, they're not that expensive. It's pretty straightforward to go to a company like Al Bradley and say, hey, we want to implement Al Bradley PLC with curriculum.